Which one do you want to start with?
We start with 6.14.
6.14. Okay, so sintering copper powder, and we're looking for the distribution of y1 times y2.
Yeah. Yeah.
All
So I
right.
get that it's method of distributions, but like once I got to step 3 and like figuring out how to integrate it with both variables, I kind of got lost. Because I know we did one of those in class and it's in my
Mm-hmm.
notes, but I I don't know. I didn't really comprehend it as much as I thought I did. So
All right. So we're for the distribution function, we're looking for the. Actually, why don't I share my screen and then we can look at a Word document. Can you see that?
yeah.
Okay. Make it bigger. So we're looking for the probability that. Is it okay if I do x and y instead of y1 and y2?
Yeah, that's what I did. I did like X is Y1. That's what
Sounds
happened.
good. So x times y is less than or equal to u.
Right.
And to help us write that as an integral, it might be helpful to write it as the probability that y is less than or equal to u over x.
Yep.
So then we want to set that up as an integral or double integral.
Yeah. I think this is the part where I kind of got lost because I usually like draw pictures and I didn't know how to draw the picture. And
Yeah, so maybe instead of sharing Word, I want to share a whiteboard and we can sketch it. All right. So our overall region for x and y is x, or y1 is between 0 and 1, and y, or y2, is also between 0 and 1. And they're independent, so we can be anywhere in this square.
yeah.
And then we want the probability that y is less than or equal to u over x. So we should sketch the line y equals u over x.
Yeah.
So if we pick a value for u, then we're going to get a curve like that. And we're looking for the integral over this region. So let's see. And yeah, as x approaches 0, y is going to be approaching infinity. As x approaches 1, that height is going to be u.
Yeah.
And so as y approaches 1, x is going to be u. So we have those coordinates. But writing either a vertical or a horizontal rectangle here is going to be a problem.
Yeah.
So what do we often do in that case?
Do the complement?
Yeah.
Instead? Okay.
So if we instead look at the integral over the sort of upper right-hand region, then we can use either vertical or horizontal rectangles. Which would you prefer?
Vertical.
All right. Okay. So for our inner integral, we're integrating along the rectangle. So we're going to have our joint density function, so the product of the marginal densities. And then that's going to be a ey. And we're going from y equals u over x up to y equals 1.
Yeah.
And then for our outer integral, we'll have a dx. And now we're thinking about sliding our example rectangle from the left to the right. So the leftmost point is at x equals u, because that's what we said the x coordinate was when y was 1.
Right.
And the rightmost point is when x equals 1. So then we'll have 1 minus that whole thing to get the integral over the actual region that we want.
Right. Okay. Okay. And then it's not like the one we did in the notes, you drew like 2 different graphs because it like the line could extend past that box or whatever. But that's not the case in this one, obviously. Because we don't have a.
If we think about changing the value of u, and I mean, you can like use your graphing calculator to try this. The fundamental shape of the region we're integrating over stays the same.
Yeah. Okay.
It's sort of, think about sliding the curve up or down.
Okay. Yeah. Cool. Okay. Then yeah, I think this one makes more sense than the one in the notes. I didn't understand the 2 picture thing. I don't think.
All right.
Cool. And then, okay, yeah, they gave us the density functions.
Yes.
Okay. So then we just integrate that and then derive it. Does that know? Okay. Cool. I think I can go from there with that one. And then what was the other one I had? The out of book problem 1.
Okay. So
that was
the insurance company, where the number of claims has a binomial distribution and the claim amounts are uniformly distributed between $200 and $600.
Yeah. So yeah, the whole double variance thing was confusing me. I don't think my code was right either, because for the code I got like 9.7, and that I don't think is right either.
I can check what I got. Let's see. What'd you say you got?
Like 9.7.
Yeah, that sounds small.
Yeah, that's what I was thinking.
Do you want to share your screen and we can talk through your code?
Yeah, I can figure out how to do that. Cool. Did that work?
Yes.
Okay. So yeah, it's just that's the second problem, but it's not right there.
All right. So let's see. You need to compare it to what the problem was. Each client will submit a claim with 1% probability. So first you're generating one random number with 1,000 clients and 1% probability. That looks good. So I see you have line 5, RUnif of X 200, 600, but you're not calling that anything. You're not putting that in a variable.
Oh. Wait, how do I do that? Do you just
say Y equals RUnif?
Oh, I see. I see. Okay, and then it'd be the sum of y then.
Correct.
Okay. Okay, because the uniform thing is using the binomial distribution, and then we're summing that instead.
Right. Yeah, because you want the total claim amount.
Okay. Cool. So then, does that look all right?
Let's see. Certainly looks more reasonable. Yeah, that looks in the same ballpark as what I got.
Okay. Cool. So then, when I did the actual computation, that's still not what I got. Because when I did the actual computation, I got 1,717, which seems close. I'm just missing a few times 10.
Okay, so maybe you're off by a factor of 1,000? All right.
The double variance theorem is kind of confusing to me, if that's what you can call it.
So I can share my Word document again.
Yeah, because like 11-31 is also the double variance, and I kind of pieced through that one and got the right answer somehow, but I don't think I totally comprehended it yet, so I want to go through this one.
Yeah. The double expectation and double variance formulas are really powerful, and they're sort of funny because they look really simple, but then applying them is more complicated. So let's see. If we use Y as the claim amount, we're looking for the variance of Y, and that will be the variance of the expected value of Y given number of claims plus the expected value of the variance of Y given number of claims. So if we know what X is, then how do we find the expected value of the total claim amount?
Let's see, I kind of figured this out. Expected value of the claim amount is Is that the uniform distribution there?
The expected value of one claim amount is going to be using the uniform distribution.
So then that would just be 400.
Good, using the uniform distribution. But y isn't the amount of one claim, y is the total amount of all x claims.
Right.
So how does y relate to the amount of each of the claims?
Y, something to do with the fact that there's like 1,000 trials here.
Right now we're ignoring that fact, and we just know there were x claims. That's what the conditioning on x is. So we know exactly how many claims there were.
Okay. Then there's so many things going on. So we know, you're saying, like, in this case we know the amount of claims.
So like, let's say we knew there were 5 claims. How would we find the total amount of all the claims? Dollar amount.
Well, you just times like the amount by 5.
Yeah, to do that more formally, we would say that this is the expected value of amount of claim 1 plus amount of claim 2 plus ... plus the amount of claim x.
Right.
But then we can split that up across the addition. So we can say it's the expected value of the amount of claim 1 plus the expected value of the amount of claim 2 plus ...
Right.
The expected value of the amount of claim x.
Oh, so it would just be 400x in that case?
Right.
Okay.
Each of these is 400.
Right. Okay. So expected value of just x is 400. Okay. Cool.
So then to find the variance of that, so the variance of the expected value of y given x is going to be just the variance of 400x. What's the next step in computing that?
Then we have to find, do we use the formula for variance to do like the expected value of? Well, can you do that here? The only other value?
I think you're making it more complicated than it needs to be.
Most likely, yes.
So if we have a constant inside the variance, what can we do with that?
Oh, then it's 400 squared times the variance of x.
Yep. And then we had that x was the number of claims. So x has a binomial distribution. So what's the variance of x?
variance, that's, let's see, 1,000 times 0.01 times 0.99, is that the formula?
Yeah,
Okay, yeah.
NPQ. Good. So that's the first part of our variance computation.
Okay. That's kind of making sense. Okay.
So then for the variance of y given x, we're doing the same thing as we did up here, but now we're looking at the variance of the sum of the amounts of each of these claims.
Yes.
So how can we rewrite that?
Is that going to be, can you split apart variance too?
When can
Or
you split
no?
apart variance?
If they're independent.
Yes. And let's
they
see.
are.
Yes, it specifically says the claim amounts are independent. So we can.
So is that going to be kind of the same thing where I find the variance of like the uniform distribution?
Yep, exactly.
Times that by x? Okay, because x is the amount.
Right,
Or
x
no.
is the number of claims that there are.
X is the number of claims, y is the amount. Okay.
Correct. In dollars. And when you're doing this, y is the amount in dollars, x is the number of claims.
Right. So then, like when we're doing just looking at x, x is the number of claims.
Mm-hmm.
But doesn't the like uniform distribution there represent the claim amounts it says? So then why are we using that for x? Just totally clear.
So you'd use the uniform distribution to find the variance of the amount of claim 1. And that's going to be the same as the variance of the amount of claim 2. And the same as the variance of the amount of claim x, because they all have the same distribution. So you just have x copies of this variance of the amount of a claim that you're adding together. So it's x times the variance of the amount of one uniform random variable.
Okay. Okay, kind of makes sense. So then, so the variance of x is 13,333.33. And so then the variance of y given x is just 13,333 times x.
Yep.
Okay, because we're taking the variance of multiple x's. Okay.
Right, you're taking the variance of the total amount of x claims. And in this part, when you've got y given x, you're treating x as a constant. Like you're assuming you know how many claims there are.
Yeah. Okay, that makes sense. So then, okay. So then the expected value of the variance then is just 13,333.3 times the expected value of x, which we already found earlier on.
Which you can find using the fact that x has a binomial distribution.
Right. Wait.
Earlier we found the variance of x.
Right. Okay. Okay, I'm getting right because at the very top when we have expected value of amount of one claim is 400, I'm getting that confused with the expected value of X itself.
No, X is the number of claims.
Okay. And just the expected value of the amount of one claim, there's no really variable thing to that.
Not as we've set it up here.
Okay.
You certainly could say that that's like Y sub 1, Y sub 2, Y sub 3, or something like that.
Yeah. Okay. Right. Okay. And then we find the expected value of X, which is 1,000 times 0.1. Okay. Cool. And then we have all we need now, right?
Yeah. Now you have all the pieces.
Okay. Let me just make sure I have it right. And yeah. Okay. Cool.
And hopefully that should be reasonably close to the empirical variance.
It looks pretty spot on to me.
Cool.
Okay.
Anything else I can help with?
If you have time, can I like go back to 11-31?
Sure.
Just to make sure I understand the double variance thing.
Yeah.
Because I did make it to the right answer in this problem, but I'm
Good job.
not totally sure how. But I think, yeah, now that we went through that one, I kind of have an organizational process, which usually helps me. Because in 11-31, all we're given is probabilities here. We're not really given, like in that problem we had, what the distribution was. Here we don't have that.
Right, because here the claim amount is a discrete random variable.
Okay. So that's different. So what I did is I kind of made like well, I tried doing like a tree thing, but I don't think that really helped at all.
Okay.
So I kind of made a table of like expected value of X given Y would be like 800, and then the probability is 0.07, and then the variance of X given Y is 210,000. It kind of went off that.
Sorry, say that again.
So I made it like a little table, and like the probability equal to 0.07, which I just gave variable Y, corresponds to the expected value of X given Y equaling 800.
That's the average
which is
of
like
the 500, 1,000, and 2,000?
Yeah.
Okay.
And then I have the variance of X given Y is 210,000.
So given that Y equals 1, that there is a claim?
Right.
Okay.
Does that work there, I guess?
That sounds reasonable. Let me see what I got.
Because then when we're taking just like the variance of 800, it's just 800 squared. If there's no variable there. But should there be a variable there?
I mean, once you get into the second part of the double expectation theorem, so where you're finding the variance of the expected value and the expected value of the variance, then you also want to be incorporating the fact that with probability 93%, 0 claims are filed.
Right.
And I guess because the claim amount then is 0, you will then have the same answer if you ignore that, but like in order to make sure that you're practicing the full double
Yeah.
expectation theorem so that you know how to apply it in the future, you want to remember that that's there.
Right, and that's what I don't think I remembered that was there.
Okay. Yeah, so I'll share my screen again. So if we make a table of the number of claims, what did you call that? What variable did you call that?
Number of claims is y, I think.
Okay.
And then like the dollar amounts are x, if I'm thinking about that right.
Okay. So y could be 0 or 1 with probability 0.93 and 0.07. So this problem is most similar to the car accident example that we did in class.
Okay.
And then...
Did we do? I don't know if I remember that.
let's see. So
oh, I see it now.
We're still looking for the variance, so we'll use our same formula from the last problem. Except now we're looking for the variance of x, so we'll swap these. All right, so for the expected value of x given y, we have we have two possible values. We have the expected value of x given y could be 0 if y equals 0, or you said 800 if y is 1?
Yeah.
All right, so now when you go to find the variance of the expected value of x given y, you can think about this expected value of x given y as being your new random variable, like z. So we could actually make a table for its distribution. So we can say the expected value of x given y is 0 with probability 0.93 or 800 with probability 0.07.
Right, yeah.
And then use this table to find the variance.
Okay. Yeah, I think that's kind of what I did for that one.
Okay.
I think I was on the right track, because then you're just yeah. Because then in that case it's just like 800 squared times or is that right?
Yeah, let's call this, say, z. So then the variance of z is going to be the expected value of z squared minus
Yeah. Okay.
the square of the expected value of z. You can find the expected value of z using the table, and then you can square each of the values of z, use the table to find the expected value of z squared.
Yes. Okay. Yeah. I got that.
Cool. And then for the other part, the expected value of the variance of x given y, similarly, you're going to have the variance is going to have two possible values depending on whether y is one or 0.
Right.
So from that, you can make another table and then find the expected value of that new random variable in the table.
Okay. Right, because then it's like, here 210,000 is the variance with probability 0.07, and then still just 0 if there's nothing.
Right. Because the claim amount is always the same if there's no claim.
Yeah, and taking the expected value of a variance that's by saying expected value, that means you're timesing it by those probabilities.
Right, because we're thinking of the variance as being it's a new random variable.
Okay.
Or it's the function of y that we're finding the expected value of.
Yeah. Okay. Cool. Yeah, I think I did the right thing. I just didn't know what I was doing, but now I understand what I did.
Okay, excellent.
Sweet. Okay. I think that's it. Cool. Well, thank you for meeting with me.
You are welcome. Have a good afternoon.
You as well.